and you look for the hotspots. Because most of the program will not, any change you make won't actually affect the overall performance. There'll only be some bits where it counts. You want to find those bits, those hotspots. Then when you've found the hotspots, you can then begin to make some transformations to see if they'll improve the performance. But even then, you look, you say, oh, I think this transformation should do something. You measure, you make the transformation, you measure again. If there's been no significant improvement, you undo the change. You use that process very rigorously as performance improvement in order to get the performance levels you want. Do that, and that will get you performance improvement. But never guess where your performance issues might be, because you'll almost certainly be wrong. As a more advanced technique, and a technique we use a lot at ThoughtWorks, make performance tests part of your regular build, run them as frequently as you can, and look for anything that causes performance to suddenly go down. And that indicates there's a problem. And 9 times out of 10, it'll be hitting the database, or some kind of remote call situation. It'll be the source of performance. It will pretty much never be something like this, which is in-memory computation. Occasionally you'll be wrong, of course, but very, very rarely. And I actually take it more strongly in refactoring in this situation. I wouldn't even bother thinking about trying to run the test, even if my spidey sense said, "Ooh, this looks like it might be a problem." Because once I've refactored the code, I'm going to be able to use the process I just described for performance improvement much more effectively. You can improve the performance of well-factored code much more easily than you can poorly factored code. And that's something that I think all of the performance gurus that I know really stress. Get the code well factored first, then do a disciplined approach to performance improvement. You'll do much better that way. So for the moment, we won't worry about it. And in fact, I'll indicate how this can improve performance later on. So, we do this. And then we look at the play, and now inside the amount for statement, we can also replace the play there with the function call. And what does that allow us to do? I'm forgetting my own script here. So this replace temp, that completes the replace temp with query. I replace it in the function as well. And what I want to point out is that this is a very definite set of steps. And if you look in the refactoring book, this is the web edition of the book, you see the refactoring, you see a brief description of it, and as you look down, you'll see this set of mechanics. And you'll notice that's describing what I talked about doing. Checking to see if we don't have any changes, and also various points at which we can test. Because not just can we always test at the end of a refactoring to make sure we haven't broken it, we can often test in the middle as well, and we should. If we have fast tests, we should be able to do that. So then once I've done that, I can apply another refactoring called change function declaration. And I can do this because that play argument that's being passed in, I don't need anymore. Because I've replaced the temp with a variable, replaced the temp with a query, I don't actually have to pass the temp around anymore. That's part of the benefit of removing temps from large methods. I don't have to worry about passing them, because instead I can just calculate them as needed. And so I will do that with the change function declaration, which just allows me to then remove it. So having done that, often in this kind of situation, I'm likely to go on a rampage against temporary variables. So here, this amount, it's used in a couple of places. What do? Replace temp with query again, and I take that up with the call to the new method that I just created a while ago, the amount for method. What's next? Oh, now I'm repeating. I see another block of code that I want to do something with, and again, I extract function on it and create a new function. We're seeing the original method slimming down as I do this. What's next? Well, I'll take another variable out. Here it's formatting. So again, I replace some rather kludgy bit of Java internationalization stuff with a simple little function call that does the whole thing and hides all that kludge away. Fairly straightforward. The next two are a bit more painful. Here, I'm looking at some overall summations done through the loop. The loop is basically calculating and summing up two values. How do I how do I replace those temps with query? Can I do that? I can, but what I do is I have to apply a refactoring called split loop. What split loop does is it basically duplicates the loop, one for each variable. If you've got people who worry about the performances of individual inline variables, now their hearts are really palpitating. But again, I'm only looping over what? A dozen things? I mean, it's not a big deal. And again, as we'll see, later performance improvements, a performance improvement step later on will be much more beneficial. I'm not quite in a position to extract here because my initialization code is separate from the for loops. So I use another refactoring, which is slide statements, and I use that to slide the code so that I've got all the code I need to extract together. Slide statements is an interesting case. It wasn't in the original book because I considered it too trivial to be worth mentioning. Oh well, that was a mistake, and I decided to put it in the new book. So once I've slid the statements so that they're close to each other, I can then extract those functions. So, what does this leave me with? The overall statement function and a whole load of functions that I've extracted in the process. Notice something about that remaining statement function. That function now is all about just the formatting and the laying out of that statement. None of the calculations are in there. All the calculations have moved to the functions. This is a very important separation if I'm going to support a different output format, right? Because now I could easily see how to replace with an HTML version. The question is, how do I do that replacement in a way that properly separates the structure? Because I've got a whole bunch of nested functions in there. If I wanted to create a new HTML statement function, I'd have to copy all the nested functions over, and that would not be nice. Fortunately, there's a few different techniques that I can use to do this. The one I'm going to mention is one called split loop, or sorry, split phase. Split loop was the one I would previous. Now, split phase is another new refactoring that I didn't include in the first book. It's a bit more interesting as to why I didn't know. I never even thought about this as a refactoring. It was only a few years ago I was visiting Kent Beck, and we were chatting, and he talked about how he'd identified this refactoring called split phase, and he described it to me. And it was one of those moments when somebody tells you something you've known for 10, 15 years, and he's just given a label to it, and you go, oh, I do this all the time. I've been doing this since I ever started programming. It's really important. Why did we not give this thing a name? Because if we don't give it a name, we can't talk about it. And split phase is a really powerful technique that you've all probably used tons of times, but perhaps not thought about as a thing, and a thing to talk to other people about doing. And that's why it's such a powerful thing. Basic idea of split phase is to say, at some point you've got a bunch of computation, but you can divide it into two phases, one followed by the next, where the first phase creates some intermediate data structure, which it passes on to the next phase. If any of you remember your compiler theory classes, you'll know about tokenizers, tokenize text into tokens, which is an intermediate data structure, but it passes on to a parser to create a parse tree. And that itself, of course, is an intermediate data structure for further layers of transformation. We do this all the time. And I just hadn't thought about it as a thing. But this conversation with Kent brought it out. So let's go through the split phase refactoring and how that works. So basically we begin with the statement that we have. And the first thing we do is we extract the entire content of the statement into its own function, which seems like a silly waste of time, but trust me, this is the good first step. So now we've got all of this code separated into its own function. The next thing we do is we create this intermediate data structure. which for the moment is just an empty dictionary, an empty JavaScript object. Doesn't really do anything, and we add it to this render plain text method. In time, we'll get rid of the other two arguments to render plain text and only use this intermediate data structure. Then, what do? We start populating the intermediate data structure. So here, we're just saying the statement data's customer is the invoice's customer. Very simple, straightforward thing. And we replace all the references to invoice customer in the render plain text with data.customer. This is a very, very simple refactoring, but it's the essence of what we're trying to do. Move all the data from the original arguments into this intermediate data structure. Then, we do the same thing with the performances. We take the performance object, data structures, and we put those onto the data structure, and now we can get rid of invoice as one of the input parameters to render plain text. Notice as part of doing this, we do have to class this data object into one of these further functions as well. And I'm not showing the details of that because otherwise it would take too long. Now, the next thing we want to do is we want to look at these performance structures, and we want to say, at the moment we're passing in the original performance. What we want to do instead is create, again, an intermediate data structure for this. So what we do is we do this little, we basically copy the performance into a fresh object. And I use the term enrich because, as we'll see, we'll add more data to this intermediate structure again. So what we're doing is essentially copying the input and then adding in some of the computational stuff. So perhaps this will be a bit more here when we see this. So here we say, okay, we take each performance and we do that play-for lookup and we move it from the rendering of the plain text into the creating of the intermediate data structure. We add it into that intermediate data structure. And that causes us to move one of our nested functions from the rendering into the calculation part of the code. And then we just continue doing that. We do the same thing for the amount form. We calculate the amount in creating the intermediate data structure, and it allows us to move the function from the rendering part to the calculation part. We just basically repeat that whole process, moving the function steadily one at a time, till all of the calculation functions are in that top part, the first phase of the calculation. They populate the intermediate data structure, and the intermediate data structure is then passed on to rendering as text. Now, at the moment that works fairly well, but I've got a big block of code there. So what do I want to do? I want to turn it into its own function. So now we see the two phases are very clearly separated. Creating the statement data does all the calculations, render plain text renders the function, and then the overall statement function just glues the two together with a simple bit of function call. Once I've done that, creating the HTML version is pretty straightforward. All I have to do is create a new render HTML method. I pass the same statement data into it using the same code, and it's easy to do. And in fact, if I wanted other output formats, I would just easily create those on top of it. This also shows the point of the performance. If there is slow performance as part of that calculation, what I've done by doing this is I move that to the creation of the intermediate data structure. That intermediate data structure, if it's expensive to calculate, I can cache. I can cache it in memory, I can cache it on disk, I can do whatever I want with it. But I can only do that performance improvement because of the fact that I broke the program down into smaller pieces and was able to arrange them into this nice two-phase computation. So this is a good example, I think, of how refactoring can give you more levers to improve performance, and why it's so much better to get a well-factored program and then do the performance tuning on that. You'll notice as part of this I lifted that little USD calculation function to the top level so that it could be used easily by the HTML and the plain text versions. But that's basically the story. And the key thing to remember here is all of those steps that I took were small refactoring steps. Even a big refactoring like split phase is really broken down into small individual refactorings, each of which you can do and the program still works. You do, the program still works. This is the essence of refactoring. Lots of small changes. The program is never broken, but over the course of time, you get the finished spot. And even for a small program like this, if I had to make that change, I would probably do it that way, because I actually went through that pretty fast. It takes longer for me to explain it than it does to actually do it. It's a pretty quick process to go through, and I have a much more straightforward task. Because now, if you think about what you'd have to do to create the HTML version of that code without having refactored it first, you would involve a lot more thinking to get there. And now I have a better structure for more output forms. So that's really what I wanted to give as an introduction. If you go to the introductory chapter that you can download from that second link, you'll see how I deal with the multiple types, essentially by introducing an object-oriented inheritance structure, which works quite well for this case. That then leads into the rest. But perhaps the most important thing to take away from this is how I've used the example to help explain the concepts. That I can take a particular piece of example, step back and talk about a general principle, and then come back to the example. And the example kind of anchors the discussion. That was why I chose to open the book with an example, and that's why in teaching many things, I like to use examples to drive things. So that's something to think about. Of course, when you're working with people on your team, you can use your own code as your example to help drive things through. The examples really help get points carried through. So I hope you found that useful and interesting. Now I've got a bit of time for questions.
Thank you very much, Martin. It's always good to hear about how to write good code in the technical sector. It's also very inspiring. Well, I guess some of the most popular questions, they go beyond refactoring code, but anyway, they're the most popular ones, so let's have a look at them. So the first one is, besides refactoring, what are some of the most important engineering practices that you think are valuable for building good software?
Well, refactoring is also, I think of it as a center of a cluster of key practices. A very important one is being able to write self-testing programs. I didn't really talk about, I talked about run the tests from time to time, waving my hands because I didn't have much time to talk about it. But to do refactoring effectively, you want a solid base of tests, so that if you make a mistake, you can be confident the tests would fail and give you an indication what went wrong. Test-driven development is a great way to do that. It's not the only way to do that, but it's one of the most effective ways to do that. So I'm a big fan of test-driven development as part of that. When you're working in refactoring, and you've got a team that's doing a lot of refactoring, one of the things that people are concerned about is, how about if I'm refactoring the program over here, and it breaks what you're working on? And the way we deal with that is continuous integration. That at frequent intervals, at least once a day, I integrate my code with the main line, you integrate your code with the main line, and if I do anything that breaks your code, you find out right away. It's very popular these days to use feature branches that last days, or even weeks, or even months. But the problem is, if you refactor on a feature branch, he doesn't know about it until both of us have pushed. And by that time, you've got several days worth of work, or several weeks worth of work, and that's a big change and very difficult to deal with. That's bad because then you've got a horrible merge to go through, and we'll be shouting at each other about the merge. But what's really bad thing is that discourages both of us from doing refactoring in the future. And we have observed this, that teams that do have these kind of longer running feature branches, they tend to not want to refactor because they're worried about breaking things for everybody else. But on the other hand, if you commit to mainline all the time, and I mean, I would do so immediately after doing that split phase, for instance. I would commit to the mainline. But I could commit any time because it's always working. I could be halfway through that exercise I just showed you and commit, and I've not broken anybody. Right? So commit frequently into the main, push it to the main line, and then we all integrate, and he can see what I'm up to. And if I'm doing something that's treading on what he's doing, he finds out right away, he can come over and talk to me. So continuous integration, done properly, which is everybody commits to the main line, pushes to the main line at least once a day. That's a very essential technique for this.
Okay, thank you. There's another one more at the systems level. So when you have legacy systems, how do we know when we should take a refactoring approach or recreate?
Well, that's much more. I think it's hard to come up with good guidelines for this. It's a much more judgmental thing. It depends on the structure of the code, the kind of environment you're working in, whether the thing has got decent tests, how hard it is to produce those tests. These are the kinds of things that you've got to look at. I've never really come up with or seen someone come up with a good set of guidelines for that decision. It's not an easy decision. I think that more people underestimate how much you can do with refactoring than don't, simply because they're less experienced with refactoring. But as you get more experience, you get more confident of what you can do with a code base and using some of the more sophisticated techniques like branch by abstraction and the like. But it's never a straightforward choice because there's just so many variables and it's difficult to try and pull them all together.
Okay, thank you. One interesting question, but very popular. What is the toughest decision you've ever made in your career? Any funny stories about that?
Gosh, I don't know, that's a tricky question. I don't tend to worry too much about the decisions I've made in the past. Joining Fowler was a tough decision actually at the time because I was a successful independent consultant. I had long previously promised myself I would never work for a company again. And then I found this really nice company and that broke all the rules of what I expected from corporate behaviour. But that was a difficult decision. I remember I spent a good amount of time thinking, do I want to work full time in this outfit? And I thought, well, yeah, I'll give them a chance, see how they are after a couple of years or so. That was 20 years ago.
All right, and so about the relationship between refactoring and automated tests. Is refactoring without automated tests a bad idea?
Most of the time, yes. You really want to have good tests if you're going to do refactoring. The reason I say most of the time, there is a little group of people that are working on what they call provably correct refactorings. And it's actually a group, Arlo Belshi is part of the name to search for. And what they do is a very small set of refactorings, and they're very careful about mechanics to really lower the chances of introducing an error. You've got to be very careful when doing that kind of work. But in some situations where you just don't have the tests to work with, that kind of technique can be quite valuable. And at least they feel they've made good progress. I don't talk about it much in the book because I think at the moment it's a very niche thing, and it really needs a very high level of skill and of discipline to pull it off. So most of the time you've got to focus on getting good tests, because I think for most of us that's what we need to be able to do it.
Okay, and the final question. So how does refactoring meet microservices? It's part of, is it part of the same concept? Is it on different
they're totally different concepts. Microservices is an architectural pattern. Refactoring is a technique. The two don't really go together. The only kind of thing that I would say about the connection of the two, however, is, like many things, microservices makes it somewhat easier to refactor within a service, but much harder to refactor across services. And indeed, this is one of the reasons why many microservice enthusiasts, if I count myself as such, and I know you feel similarly, say most people should not be using microservices. And that's because it's much easier to refactor across a large monolith that's a single code base than it is between microservices that are independent code bases with calling patterns. And one of the biggest problems in microservices is once you've made the splits, refactoring across the splits is much harder. So you've really got to get those splits right. And if you're unsure where the splits are, you'd better stay with the monolith. And that's one, so that definitely is a factor to bear in mind between the two. But they are strictly separate techniques. I mean, they're definitely apples and chihuahuas.
Well, thank you very much. It's a great pleasure hearing from you. Thank you so much for being with us today.